Welcome to this coding walkthrough. In this video, we'll tackle LeetCode problem number 1958, check if move is legal. This problem involves analyzing moves in a reverse-like game to determine if they are valid based on the rules of the game. We'll break down the problem, explore different approaches, and discuss their complexities. Let's dive in. The problem involves a game board represented as an NXN matrix, where each cell can either be empty, contain a black piece denoted by B, or a white piece denoted by W. You are given the coordinates of a move, specified by R move and C move, which correspond to an empty cell where a white piece, W, will be placed. The goal is to determine whether this move is legal. A move is considered legal if, after placing the white piece, there exists at least one straight line of at least three pieces, including the piece just placed, where the first and last pieces in that line are of opposite colors. If such a line exists in any direction, the move is legal, and you should return true, otherwise, return false. The board is provided as a 2D list of characters in Python or a 2D array of characters in Java. The move's row and column indices, R move and C move, are integers that specify the position where the white piece will be placed. The output is a Boolean value, return true if the move is legal, and false if it's not. To better understand the problem, let's go through some examples. In the first example, we are given a board where a white piece is placed at position 4, 3. This placement forms a vertical line of at least 3 pieces, which includes the newly placed piece and extends through the cells 3, 3, 4, 3, and 5, 3. The first and last pieces in this line are of opposite colors, B at 3, 3, and W at 5, 3. Since this satisfies the conditions for a legal move, the function would return true. In the second example, a white piece is placed at position 4, 4. However, there are no directions where a straight line of at least 3 pieces can be formed, with the first and last pieces being of opposite colors. Since none of the conditions for a legal move are met, the function would return false in this case. In the third example, a white piece is placed at position 1, 1. This placement creates a diagonal line of 3 pieces, from 0, 0 to 2, 2, including the newly placed piece. The first piece in this line is W, and the last piece is B, meeting the condition that the ends of the line are of opposite colors. Therefore, this move is legal, and the function returns true. To ensure your solution handles all edge cases, consider testing scenarios such as the smallest possible board size of 4x4, where the move is near the edge of the board. Verify cases where no legal moves are possible, as well as situations with the maximum board size of 500 by 500 to ensure efficiency. Additionally, test cases where multiple directions form valid lines, or where the board is mostly empty except for the move being made. These tests will help confirm that the solution works correctly across a variety of inputs. To approach this problem, we first need to clearly understand the rules of what constitutes a legal move in the game. The challenge is to determine if placing a piece either B or W on a specific empty cell of the board will flip at least one opposing piece in any straight line. These straight lines can be horizontal, vertical, or diagonal. For a move to be legal, 3 important conditions must be satisfied: the cell must be empty, the new piece must initiate a line of contiguous opponent pieces, and this line must end with another piece of the same color as the one being placed. Essentially, the move must create a valid sequence where at least one opponent's piece gets flipped. Keeping these rules in mind will guide our solution design and implementation. One straightforward way to solve this problem is by using a brute force approach. The core idea here is to systematically explore all 8 possible directions from the chosen cell and check whether any of these directions meet the flipping criteria. We start by verifying that the chosen cell is empty, as placing a piece on an already occupied cell is not allowed. Next, for each direction, we move step by step to examine the sequence of cells. During this traversal, we keep track of the opponent's pieces we encounter. If we hit the board boundary or come across an empty cell, the direction is invalid. However, if the traversal ends with a piece of the same color as the one being placed and at least one opponent's piece was encountered along the way, then the move is valid in that direction. If any of the 8 directions is valid, the entire move is legal. While simple to implement, this approach can be computationally expensive since it involves traversing large parts of the board multiple times, especially in edge cases where no valid move exists. While the brute force approach is simple, it has its drawbacks due to redundant checks and unnecessary computations. This is where an optimized approach using directional pruning comes into play. The fundamental idea here is to avoid exploring directions that are clearly invalid from the very beginning. For example, if the adjacent cell in a particular direction does not contain an opponent's piece, we can immediately skip that direction altogether. This saves time and reduces the number of unnecessary traversals. The steps are similar to the brute force method. We still verify the initial cell and iterate through potential directions. However, we now incorporate an early pruning step, checking if the immediate neighbor is an opponent's piece before proceeding further. If a direction remains valid, we continue traversing, ensuring the sequence ends with a piece of the same color as the one being placed. This optimized approach reduces the overall number of computations by eliminating irrelevant directions early, making it more efficient for practical scenarios. The optimized approach with directional pruning is the chosen strategy for solving this problem, as it strikes the right balance between efficiency and implementation simplicity. The key observation driving this method is that a legal move requires flipping at least one opponent piece, which means the immediate neighbor in any valid direction must be an opponent's piece. By leveraging this insight, we can prune invalid directions early, avoiding unnecessary checks and improving runtime performance. This efficiency makes the optimized approach particularly well suited for larger boards, where brute force would struggle due to its higher computational cost. While slightly more complex to implement, the directional pruning strategy remains straightforward to understand and debug. Ultimately, this approach ensures scalability and clarity while delivering significant performance benefits, making it the most effective solution for this problem. To determine if a move is legal in this game, we start by parsing the input. The game board is represented as a 2D grid, where each cell contains either B for a black piece, W for a white piece, or dot for an empty cell. Along with the board, we also receive the player making the move, which will be either B or W, and the target position, given as coordinates X, Y, where the player intends to place their piece. Once we have the input, the first step is to perform some initial checks. We verify that the target cell is within the board's boundaries and that it is currently empty. If the cell is not empty, then the move is immediately deemed illegal. Additionally, we need to define the directions in which the move could potentially flip pieces. For this game, there are 8 possible directions to consider: horizontally to the left or right, vertically up or down, and diagonally in all 4 directions: top left, top right, bottom left, and bottom right. These 8 directions can be represented as pairs of changes in X and Y coordinates, or direction vectors. For instance, moving left corresponds to -1, 0, moving right is 1, 0, and so on. We can represent all the directions as a list of tuples in Python. Directions equals -1, 0, 1, 0, 0, -1, 0, 1, -1, -1, -1, 1, 1, -1, 1, 1. Next, we iterate over each of these directions to evaluate whether the move is legal. For each direction, we start at the target position, X, Y, and move step by step in the current direction. First, we check if the adjacent cell contains the opponent's piece. If it doesn't, we can immediately skip this direction. If the adjacent cell does contain the opponent's piece, we continue stepping further in the same direction until we either encounter the player's own piece, which would indicate a valid line for flipping, or we go out of bounds or hit an empty cell, which would invalidate the line. Once we've iterated through a direction, we evaluate whether it meets the flipping condition. Specifically, if we encounter the player's own piece after traversing at least one piece belonging to the opponent, we can mark this direction as valid for flipping. We keep track of all valid directions where flipping occurs. At this point, we can make the final decision about the move's legality. If at least one valid direction is found, the move is legal because it results in flipping at least one line of opponent's pieces. Otherwise, it is illegal. This logic highlights a few key insights. First, a move is only valid if it traps at least one line of opponent's pieces between the new piece and an existing piece of the same color. Second, the use of direction vectors simplifies the algorithm, as it allows us to handle all 8 directions uniformly. Additionally, we can optimize the algorithm with early termination. Once we find one valid direction, we don't need to check further if we only care about legality. Finally, edge cases, such as placing a piece on a full board or making a move that doesn't flip any pieces, must be handled carefully to ensure correctness. To implement this algorithm efficiently, we rely on a 2D grid to represent the board, which provides constant time access to any cell. The use of direction vectors, an array of 8 tuples, ensures that we can iterate over all possible directions without redundant code. In terms of complexity, the time complexity is O, k*d, where k is the number of cells on the board, and d is the fixed number of directions, 8, that we need to check. This considers both the input parsing and the directional checks. Space complexity is O(1), because the algorithm uses a fixed amount of additional memory, regardless of the board size. To better understand how this works, let's walk through an example. Imagine the following board configuration: BBW, BWW. W. The player B wants to place a piece at position 2, 0. First, we check if the target cell, 2, 0, is empty. It is, so we proceed. Next, we define the direction vectors and begin iterating. For the direction 0, 1, which moves right, the adjacent cell contains no opponent pieces, so it's invalid. Moving to 1, 1, which is bottom right, we find a valid line. The piece at 2, 1 belongs to the opponent, and further along the same direction, we encounter the player's own piece, making this line valid for flipping. For the remaining directions, none lead to valid flips. Since we found at least one valid direction, the move is legal. Here, we begin implementing the solution by defining a function checkMove within the solution class. This function takes 4 arguments: board, representing the game board as a list of lists, rMove and cMove, which indicate the row and column index of the proposed move, and color, which represents the player's color. Inside this function, we define a helper function called is_valid_direction to determine if a move is valid in a specific direction. This helper takes 2 arguments, dx and dy, representing the direction of movement in terms of row and column offsets. The helper function starts by calculating the next position using rMove plus dx and cMove plus dy. It also initializes a flag, found_opponent, to track whether an opponent's piece is encountered. The while loop then ensures that the position remains on the board by checking the boundaries. If the position is empty, indicated by a dot, the function immediately returns false. If the piece at the current position matches the player's color, the function checks if any opponent's piece was encountered along the way. If so, the move is valid, and true is returned. Otherwise, the loop continues moving in the specified direction, updating the position and the found_opponent flag as needed. Once the loop ends, the function defaults to returning false if no valid move is found. After defining the helper function, we check if the target position on the board is already occupied. If it is, we immediately return false since a move cannot be made on an occupied square. Next, we define all possible directions in which a move can be validated. These include vertical, horizontal, and diagonal directions, represented as pairs of offsets in the directions list. The code then iterates over each pair of directions using a for loop. For each direction, the is_valid_direction helper is called to verify if the move is legal in that direction. If any direction returns true, the checkMove function immediately returns true, signifying that the move is valid. If none of the directions validate the move, the function finally returns false, indicating that the move is not legal. This implementation efficiently checks all potential directions while adhering to the rules of the game. Here, we start by defining the checkMove method, which will determine whether a move is legal on the given board. The method takes a 2D character array board, the row and column indices of the move, rMove and cMove, and the player's color as inputs. Inside this method, we define a helper function called isValidDirection. This function is designed to check if there is a valid sequence of opponent pieces in a specific direction that ends with the player's own piece. It takes the direction as parameters dx and dy, which represent the change in row and column, respectively. The function starts by calculating the next position from the given move and initializes a Boolean foundOpponent to track if we encounter any opponent pieces along the way. As long as we remain within the bounds of the board, we check the contents of each cell. If we encounter an empty cell, the sequence is invalid, and we return false. If we encounter a cell with the player's color, the move is valid only if we previously found at least one opponent piece. If neither condition is met, we continue moving in the specified direction. Finally, we ensure that the target cell for the move is empty because a move can only be placed on an open spot. If it's not empty, the method immediately returns false. Now, we define the possible directions in which we can make a move. These include vertical directions, horizontal directions, and diagonal directions. Each direction is represented as a pair of integers in the directions array, where the first value corresponds to the change in the row and the second value corresponds to the change in the column. For example, -1, 0 represents moving up, 1, 0 represents moving down, and so on. Next, we iterate through each direction using a for each loop. For each direction, we extract the dx and dy values and pass them to the isValidDirection helper method to verify if that particular direction allows a legal move. If at least one direction returns true, the move is considered legal, and we immediately return true from the checkMove method. If no valid direction is found after checking all possible options, we return false to indicate that the move is not legal. This implementation ensures that we comprehensively evaluate all possible directions while keeping the code modular and readable. To determine if the move at 3, 2 is legal, we begin by checking if the cell is currently empty. The function checkMove ensures this by verifying that board 3, 2 equals dot. In this case, the cell is indeed empty, so we can proceed to evaluate whether placing the piece here captures any opponent pieces as per the rules of the game. Now, the function defines all 8 possible directions, which include horizontal, vertical, and diagonal paths. It then iterates through each direction to check if placing a piece at 3, 2 will result in capturing opponent pieces. For the rightward direction 0, 1, the function starts at cell 3, 3, which contains B, indicating an opponent piece. Moving further to 3, 4, it finds W, which matches the current player's color. This establishes that the opponent piece at 3, 3 is sandwiched, making this a valid move. As soon as a valid direction is confirmed, the function returns true, indicating that the move is legal. In this case, we are checking if the move at 4, 0 is legal. The checkMove function first verifies that the cell is empty, which it is since board 4, 0 equals dot. The function then defines all 8 possible directions and evaluates each one. For each direction, it looks for a sequence of opponent pieces followed by a piece of the current player's color. For example, in the upward direction, -1, 0, starting from 3, 0, the function finds the cell to be empty, making the direction invalid. This process is repeated for all other directions, but none of them result in capturing any opponent pieces. Consequently, the function returns false since no valid direction is found, and the move is deemed illegal. Here, we are evaluating the move at 5, 0. The checkMove function begins by confirming that the cell is empty, which it is because board 5, 0 equals dot. The function then explores all 8 directions. For the diagonal direction, -1, 1, upward and to the right it starts at 4, 1, where it encounters W, an opponent piece. Moving further to 3, 2, it finds B, which matches the current player's color, thereby sandwiching the opponent piece at 4, 1. This confirms that the move captures an opponent piece, making it valid. The function returns true to indicate the legality of the move. To evaluate the time complexity of the checkMove function, we begin by considering the outer loop, which iterates over the 8 possible directions such as vertical, horizontal, and diagonal. Since this number is constant, the cost is O1. Next, within the is_valid_direction function, the traversal for a single direction starts from the given position and moves step by step until we either encounter an invalid cell, a valid move, or the board's boundary. In the worst case, this traversal can span up to 7 cells, as the board is 8 times 8. However, 7 is a constant value, so the cost per direction is O1. When we account for all 8 directions, the overall time complexity becomes O8 multiplied by O1, which simplifies to O1. This demonstrates that the time complexity remains constant, regardless of the specific board configuration. Now turning to space complexity, the checkMove function does not use any data structures that grow with the input size. The only additional memory usage comes from a few variables such as x, y, found_opponent, and the directions list, which are all constant in size. This results in an auxiliary space complexity of O1.
Additionally, since the function does not use recursion, there is no extra memory consumed by the call stack.
Therefore, when combining these two considerations, the overall space complexity for this function is 1. This highlights that the function is highly efficient in terms of memory usage, as it does not require space that scales with the board or any other input. To better understand the efficiency of this approach, let's compare it with a naive solution.
A less optimized method might involve scanning the entire board to determine if any valid move exists.
Since the board is 8 × 8, such an approach would involve 64 cells, leading to a time complexity of n squared, or 64, in this specific case. In contrast, the optimized implementation focuses only on the 8 possible directions and evaluates up to 7 cells per direction, which is significantly more efficient. This optimization reduces the time complexity to 1, showcasing the advantage of targeting only the necessary cells and avoiding unnecessary computations. Analyzing the function across best, average, and worst-case scenarios further reinforces its efficiency. In the best case, a valid move is found in the first direction checked, resulting in minimal computation.
However, since the number of directions is constant, the time complexity remains 1. In the worst case, all 8 directions are fully explored, with each requiring traversal of up to 7 steps.
Despite this, the time complexity remains 1, because the operations are bounded by the constant size of the board. Similarly, the average case is unaffected, as the number of directions and board size do not vary. This consistency across all cases highlights the robustness of the function's performance. Finally, a mathematical proof of the big O complexity solidifies our conclusions. The board size is fixed at 8 × 8, meaning the number of cells and directions is constant. For each direction, traversing up to 7 cells involves a predictable and bounded number of operations. Furthermore, the input board configuration does not affect the function's behavior, as the board size itself is unchanging. Since both the number of directions and the traversal limits are constants, the function's operations do not scale with input size. As a result, both the time and space complexities remain 1, underscoring the efficiency and scalability of this implementation.
When tackling this problem, there are several common mistakes to watch out for. One major issue is failing to check all possible directions.
Since the move's legality depends on horizontal, vertical, and diagonal checks, missing even one direction can lead to incorrect results for edge cases. To address this, you can use a loop or a helper function to systematically verify all 8 directions.
Another frequent mistake involves out-of-bounds access. As you iterate in a given direction, it's crucial to ensure that your indices remain within the board's boundaries. Without proper bounds checking, you might encounter runtime errors.
You can prevent this by using conditions like 0 = x less than n and 0 = y less than n before accessing the board. Lastly, flipping pieces incorrectly is another pitfall. Some solutions attempt to flip pieces without first confirming that the move is valid, leading to inaccurate board states. The right approach is to validate the move by traversing all directions and only flip pieces if the move passes the checks.
Another common challenge is overlooking edge cases.
For example, moves on the borders, or scenarios where the board is nearly full or empty, can be tricky to handle. To avoid surprises, make sure to test your solution with a variety of inputs, including corner moves, edge cases, and invalid inputs.
Inefficiency in direction checks is another area where candidates often struggle.
Recalculating the same directional offsets repeatedly, often with nested loops, can slow down your solution significantly. A better approach is to predefine direction vectors, such as directions equals 0, 1, 1, 0, and then iterate over these vectors directly. This not only simplifies your code but also improves its performance.
This problem also provides some valuable insights for interviews.
A key takeaway is the importance of systematic iteration, traversing all directions methodically and handling edge cases carefully. Interviewers typically appreciate clean, modular code, so consider using helper functions for direction validation to reduce redundancy.
This demonstrates thoughtful design and good coding practices.
If your solution doesn't work as expected, a useful debugging strategy is to test each direction individually.
This helps isolate where the error might be occurring.
Additionally, be prepared for follow-up questions from interviewers. They might ask you to optimize for larger boards or adapt your solution to other grid-based problems, such as finding words in a grid. This is an excellent opportunity to showcase your ability to generalize and extend your approach. If you're interested in related problems, there are several others that involve similar grid traversal techniques. For instance, LeetCode 130, Surrounded Regions, uses comparable mechanics to identify regions that need to be flipped. LeetCode 200, Number of Islands, focuses on systematic exploration of grids using depth-first or breadth-first search. In LeetCode 529, Minesweeper, you're required to uncover cells while carefully managing bounds checks, a challenge that feels similar to this problem. Another related problem is LeetCode 1020, Number of Enclaves, which also emphasizes connected components and grid traversal. By practicing these problems, you can build a stronger foundation in handling grid-based algorithms. There are also alternative approaches you can consider for this problem. The brute force method involves checking all directions for every move and marking the move as valid if any direction results in flipped pieces. While this approach is simple to implement, it becomes inefficient on larger boards because of repeated checks. A more optimized strategy is to use pre-computed direction vectors to minimize redundant calculations. This method improves efficiency and keeps your code modular, though it may require slightly more effort to set up. Another technique is the simulation-based approach, where you simulate the move, keep track of the flipped pieces, and roll back the changes if the move is determined to be invalid. This approach is particularly useful for debugging but may require additional memory to store intermediate states. Each of these methods has its trade-offs, and the best choice depends on the specific requirements and constraints you're working with. Great job following along. To wrap up, we discussed the problem of validating moves in a Reversi-like game. Key concepts included 2D grid traversal, direction-based logic, and edge case handling. These skills are highly transferable to other grid-related problems. Thank you for watching. Don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!